Hello everyone. This talk is about fully context-aware video prediction. My name is Byeon and I'm from NVIDIA Research. So it seems that everyone has a microphone, but I didn't say I won't have it. So if someone cannot hear well, just let us know. And they are my co-authors. So video prediction is a task given a video, predicting future frames pixel by pixel. Recent approaches mostly use convolutional LSTM or 3D CNN's SL-based model. Their main focus is to reduce the blurry predictions like this. And there are some solutions proposed so far. The first direction is predicting pixel motions or optical flow. Another direction is explicitly modeling moving foreground objects separately from the background. In this case, videos contain mostly the static background. Similarly, Villegas proposed a model decomposing the scene, the contents, and the motion. Lastly, more sophisticated loss functions or adversarial training are used. In this study, we try to ask the question, what fundamentally causes blurry predictions? There are two answers we found. The first is the future may be ambiguous given the past. And then the current models do not utilize all available information from the past. So in this talk, we will focus on the second part. Let's first have a look at the convolutional LSTM for video prediction. Let's say we want to predict the red pixel is the one that we want to predict. And convolutional LSTM will see the blue pixels, but not the gray ones. So as you can see that the closer frames to the future, the more missing pixels. This week, we call this blind spot problem. But what we want to do is like this. So we want to collect all the information using all available pixels. To do so, we propose a fully context-aware video prediction model. So first, this is the same operation as a convolutional LSTM between frame t-1 and t. So there is a recurrency in time direction. So this is the same operation as a parallel multidimensional LSTM along the time dimension. So from now, I will call this operation as PMD. And also, we can apply this operation in other directions too, like width or height directions for videos. So these illustrations show that how pixels are connected for width minus directions and height minus directions. And we can do the same. For the opposite directions too. So in width minus direction, the information flows from left to right, and the height minus directions, information flows from top to bottom. So if we do the opposite directions, which will be the W plus direction, that will be from the right to left, and for H plus cases, it will be bottom to top. In this way, it can cover full available context without having a deep model. So this is our architecture. I will explain one by one. The first is the parallel MD-LSTM blocks I already explained before. So it has 5 PMD blocks with full 5 recurrent directions. And then the output of all directions are combined in context blending blocks. So there are 2 blending blocks we compared with. The one is a uniform blending. It's simply the it simply adds the output of the all directions. And weighted blending contains the learnable weight for each direction. So the first two, the PMD block and the context blending block, are the one layer. And for video prediction task, we use up to 4 layers. So this is our final architecture. It's a stack of 4 PMD and context blending blocks. Plus, we added the 2 skip connections. These skip connections helped us fast convergence. Additionally, we added the regularization via directional weight sharing between H minus and plus blocks and the W minus and W plus blocks. And then our loss function is L1 plus gradient difference loss. So this is our final architecture. Let's first have a look at the ablation study to understand the effect of the different combination in architecture. We consider the 4 different vectors. One is the number of layers. And second is the blending types, either uniform or weighted, or the use of directional weight sharing, and then the size of the model. Then we found that the increase of the number of layers improved the performance with the weighted blending and the directional weight sharing. And our big model has a slightly better PSNR than the small model, but small model has a lot less, fewer number of parameters. So we kept both of them to have further comparison. So the main advantage of our model is that it can cover the entire context more efficiently. So we create the baseline that has the very deep model. So ideally, it should have the full context too. So we will compare this baseline with our model. So instead of having 5 directional blocks with the 4 layers, it has a stack of 20 convolutional LSTM layers plus 2 skip connections. And the number of parameters is comparable to our best model. And surprisingly, it outperforms almost all the state-of-the-art models. The fact that our baseline works so well shows that more context helps. But still, our ContextVP performs better than this baseline with the similar number of parameters. And also, ContextVP is more suitable for parallelization since both pixel and the direction level of parallelization are possible. So let's look at the comparison now. The first one is the next frame prediction given 10 input frames. It's trained on Kitty dataset and tested on Kartek pedestrian datasets. So pictures on the bottom, you can see some examples of Kartek pedestrian dataset video frames. We compared our model with the copy loss frame and 3 recent approaches and our baseline. And our baseline outperforms all 3 approaches, and our method outperforms the baseline. And this is a visual comparison. So as you can see that ours is closer to the ground truth compared to the other 2. And in this example, the car in the front is almost as sharp as the ground truth, but the car in the back is quite blurry. The main reason is that this car didn't appear in the input frames. So it happens the same for the other approaches too. So that's mainly due to the future ambiguity. And this example is similar. The front car is sharper, but the car in the back is blurry for all of them. Yeah, I just realized it's a bit blurrier here. So next is the multi-frame prediction on UCF11 dataset. It used the 4 input frames. So those input frames are used in whole datasets. It's just consistent to other comparison. So I just use the same as others approaches. So this is trained for next step prediction, and then tested to recursively predict 8 future frames. As you can see that the baseline has some deformation on the bow, and the MCNet has a slight artifact on the elbow of the guy. And ours can capture a lot better motions than the other two. And this one, this example is one of the most challenging ones in this data set, because it has both huge camera motions and the motions from the players. So as you can see that eventually all 3 methods kind of failed, but it has very different behaviors. So first, for MCNet, it tried to capture the camera motion, but it has a huge deformation. And the baseline model tried to capture the motion of the players, but the background is almost static. And ours tried to capture both camera motions and the motion of the players, but eventually over time it has a larger deformation. In conclusion, ContextVP resulted in improved performance without the use of separation of motion and contents, learning optical flow, or adversarial training. ContextVP enables separation of depth and contents. So increasing depth is not really necessary to cover full context. And also, more computations can be parallelized compared to very deep models. And now let's go back to the initial question, what caused the blurry predictions? So far in this talk, we covered the second part, but the first point still remains. So this hope to be addressed in the future. Thanks for listening. Our poster is number 2 in first floor, and you can please come by and talk to us, or you can also drop us email. And the bottom part is our project page. So we plan to upload the code very soon. And also, it seems the videos are quite blurry, so you can check more videos on the website. Thank you.
I think we may have time for just one quick question. Okay, so let me ask you one question. So you used forward a future prediction. Could you reverse the order of the video and look backwards? Would that help?
You mean the same trained model? If you can train it that way, and yes, we can do it. But,
and would that improve? Like, for example, with the bow, your bow didn't move with the violin.
Oh, you mean in both directions?
Yeah, both temporal directions.
Yeah, that's possible. Yeah.
Okay.
Yeah, there will be. Yeah.
Okay, thank you.
Thanks.